Okay, good morning everyone. Today we want to look at the gravitational waves in the Newtonian limit. First of all, let's just start by saying let the relative acceleration of two particles be given by the following expression, where the second rank symmetric tensor here that I have epsilon sub jk is given by this expression, that is this one here in the middle. This is the Newtonian tidal gravitational field, and that is what we're going to call it. Today we're going to be speaking more of Professor Kipton's native language. So let's so this is the Newtonian tidal gravitational field. Relativistically, the separation vector, which is that, of course, I've used an arrow to denote it here, but of course it represents either this or this, which is, or maybe even this one here, zj. So it could be zi, say, now between, so the separation vector between accelerating particles has only spatial components, and this is what we are going to be working with. Now, if all the connection coefficients and their derivatives vanish at the origin of the local Lorentz frame, and of course, if you recall, we already said that we are working here only with the spatial components, so only the spatial components of this separation vector is non-zero. This will be 0, and we've just stated that the connection coefficient here is 0, and the derivatives of that also are 0. Then it will be assumed, and of course it follows that in the local Lorentz frame, the equation of geodesic deviation, which will have to be that, explaining these terms here, a mu, or this term here, is the relative acceleration of the geodesics, of course, between two particles. So that are moving in their own geodesic, So, and then t here, t mu is the tangent vector of the geodesic, and s, by the way, is the deviation vector. So, with all these conditions that we have stated here, this equation, as we know traditionally in gravitation, simply becomes that. And as you can see, it looks almost the same with what we have just written that also here by this at this point. Okay, I think there is something here that I've missed really, which I should include, which is the fact that I have here to be zk. So this equation, the equation of geodesic deviation, of course, that's what this equation is. This equation is known as the equation of geodesic deviation, becomes this. I'm not showing any of this, I'm just moving pretty fast because this is really not where I want to dwell into this, so I'm sorry for that. Now, the tidal gravitational field, which is epsilon, or which we have defined here to be epsilon sub jk, and if you recall, we said was equal to this this factor here in this expression, which we have named this. Now you can see that if I compare this, my equation of geodesic deviation, and this one, then of course it's just a matter of comparing the coefficients, or the two equations. It therefore means that Rj0k0 is equal to that. And of course, if you recall, this is what we call our tidal gravitational field. Now we want to look at some of this, like we said, we are looking at the gravitational waves in Newtonian limit, and some of the equations we shall need in particular will be these linearized objects, the Christopher's symbol linearized or connection tensor. We've shown this and done this in detail in the past, so we're just going to call them out. This one, for instance, and the linearized version of this, or this particular one. In the Newtonian limit, we want to assume a slow motion constraint, and by that we mean, of course, that when we are differentiating the metric perturbation with respect to time, that what we obtain, the magnitude will be far less than what we will obtain when we differentiate it with respect to any of the spatial components. And of course, the velocity at this time, in this situation, also will be far less than the speed of light. And if we are assuming weak gravitational fields also, it will just mean that our metric perturbation also is far, far smaller than 1. And for a quasi-static condition, which is eventually what we shall be considering, what it will mean is the derivative with respect to time of the metric perturbation, or any object, in fact, for that matter, will be equal to 0. So then the equations of motion of a particle in a gravitational potential, which we know to be this, for instance, again, I'm not talking so much in details about this because I'm moving pretty quick to something else which I want to get very quickly to gravitational waves in the Newtonian limit. But of course, this is all pretty well known. this being equal to 0, and of course, like we stated before, that we have stated all the conditions that we're going to be applying next, and then here the metric itself has been splitted or approximated into the Minkowski metric plus the metric perturbation. Of course, when x is not, or should I say, one of these indices here for either beta or gamma being equal to 0, it means we're just talking about the time component, and if we're differentiating it with respect to tau or any of these, we get 1. So with all these conditions we have stated, the Newtonian limit, especially the slow motion constraint, which has been denoted by this and that, and the weak gravitational fields, which have been denoted by the smallness of the metric perturbation, and the static nation of this condition that we want to consider, which has to do with the vanishing of the time derivative of the metric perturbation. We want to see exactly what this equation becomes. Okay, then with our stated conditions, the very last equation we've written before becomes this. Of course, we're selecting not for the indices that corresponds to each one of these. So both of them which were contracted have been set to be equal to 0. And with our condition, of course, this being equal to 1, and this will of course imply that this expression is just this equal to 0. Now, we are going back to our linearized Christoffel symbol or affine connection. And with this expression, of course, all I have to do is on the corresponding indices on which each one of these is 0, of course, I don't have it here, but sorry, maybe you will have to just scroll back a little bit to see what I've written, but it's just a matter of substituting these indices correspondingly wherever they occur. And if you do that, and since we have already said also that we are considering a static condition whereby any derivative with respect to time will be 0, so which is why both this and this are equal to 0. And having done that, it means we are left with just this last term, multiplying the factor out there, and this is what we get. So we have here something here, the temporal part completely differentiated by, well, okay, so we could sum over nu here also, and so we'll have 0, 0 for the first term, minus, of course, this I means 1, 1, 2, 2, and 3, 3, so which has just been summarized in that form. Again, this part here is a derivative with respect to 0, and because of that, it vanishes, and all we have left is that. Of course, I could have decided to raise nu here, and it becomes alpha on top here. Well, it's all fine, because with this Minkowski metric, I'm able to raise this index, and all I've got here is alpha. So that gamma alpha naught is equal to that. And of course here, alpha is a free index. If I choose alpha to be 0, I'll have 0 all over the place here on the left-hand side. And then of course the alpha here will become 0. And if that is the case again, if you recall, we have said that in static condition, any derivative with respect to time is 0. This vanishes. And so because of that, T naught is all equal to 0. Now, if we choose alpha to be I, talking about just the spatial components this time, again, alpha here just becomes I. It's not 0 because we said the spatial components don't vanish. And then derivative with respect to spatial components. So it therefore means that this is equal to that. But this, of course, is the same thing as the grad function. So in essence, we have been able to show in these conditions that we've stated that gamma I naught is equal to minus half. Okay, I don't need to add this, but in some notations you might do that. But so this is just equal to minus 1 over 2 gradient of that, and then gamma naught of course we've shown is equal to 0. Now looking at also the linearized Riemann tensor, which again this time around I was able to write. Of course, in our slow motion approximation, where we said that this is far less than this, and it just simply means wherever we have any derivative of the metric perturbation with respect to time, it will simply be 0, it will vanish. And so just looking at this expression here, substituting correspondingly for alpha I put J, for beta I put 0, for gamma I put K, and then for delta I put 0. Doing that all correspondingly on the right hand side, and this is what we get. Of course, here, one of these has there's a time derivative here. There's a time derivative here. As a matter of fact, what's for this one because it's all just time derivative in both cases. So the first 3 terms all vanish. And I'm left with just the last one here, of course, with the factor outside. So what I've got for this object is equal to minus half h naught comma jk. And again, this, of course, as we have stated before, is simply equivalent to this double derivative or tidal gravitational field, and this is what we get. So this gravitational field here is simply equal to Rj0 k naught, and is equal to that, which is equal to minus that as we have shown here. So for a nearly Lorentz coordinates, with these approximations here that we've made, we know, of course, that if we were to perform such a transformation, an infinitesimal transformation, I'm just working here with the notation of Kipton, but it's just the same thing with what we have been doing all this while. And of course, we know that whenever we have this transformation, it induces the one on the metric perturbation in this form. So with the gauge change generators that chosen to impose the harmonic condition. So one other thing else is you're going to find Kipton called referring to this as Lorentz gauge. I'm going to stick to calling it the harmonic gauge. The harmonic gauge because it's what we have mostly in particle physics, and especially when you're doing quantum field theory on curved space-time. We meet this over and over again. One other name for it is the Dunder gauge. Well, but whatever it is, you just have to know that if you are looking at his own treatment, particularly in the theory of gravitation, the book by Misnerton and Wheeler, or the modern classical theory, or classical mechanics with Blanford, I believe, you may find him referring to this every now and then as the Lorentz gauge. So I'm going to erase this now. So like we stated, we are going to be applying the harmonic gauge on the new trace reverse metric perturbation, which is, of course, written as that. This is what we mean by the trace reverse metric perturbation. And in this harmonic gauge, the vacuum Mersenne field equation is given by that. So, whether for the trace reverse metric perturbation, this is equal to 0, and also for just the metric perturbation and not trace reversed, this is also equal to 0. Well, this can also be written as that. Yeah. Okay, now, if we orient the axis of our nearly Lorentz coordinates so that the waves are planar and propagate in the z direction, then the solution to the wave equation in the harmonic gauge becomes that. Yes, of course, if we were to use the harmonic gauge, come with me, I think this by the harmonic gauge, of course, is what we have been stating, this being equal to 0. Yeah, this index here is raised, so if I'm to write this, I'll evaluate this out when I'm summing this. The temporal part will have a minus, and then the spatial part will have a plus. Of course, if I were to differentiate this function with respect to t, this is just t, I'm going to get 1, and that's what you get. But like we have stated already, if the wave is in z direction already, you know that the differentiation with respect to either x or y will be 0. So that is why I put the letter z here, although, I think what I should have done maybe is say ddz, I think that will be more appropriate, yeah. Whereby the nu, of course, represents z. So when I perform that, this will bring down a minus. So minus that is equal to 0, and which just implies that this is equal to minus that. Now, as you can see, that with that condition which we have just shown right now, that the metric perturbation with mu not equal to minus this, we can write both the space-space component, the time-space and time-time components, just in terms of the space components. To show you what I mean, here if I were to substitute mu to be 0, then I'll have h bar not equal to minus h naught here z. That's what I'll get. But then again, of course, if I were to have substituted z here, what I'm going to get is h bar z naught equal to minus, but then h bar zz here. And this is what I'm going to get, h bar zz. So if I took this and substitute it here, I'm going to get a minus. I think I might have done this somewhere else that, okay, I didn't, but sorry, just trying to be so succinct. If you look at it again, just very simple, not here, and what I'll get is h bar not equal to minus h bar not z. Just ignore this last term for now. Now, but then if I substitute z here, so it's symmetric, it wouldn't matter, so it will become h bar z not equal to minus, but then zz here. And since h bar z naught is equal to that, remember we had minus h bar not z. And so I can substitute with what I have obtained here for this in this expression, and I'll get it to be in terms of just zz. What this just means is this is a time-space component, which we have been able to write in terms of space-space component. And this is a time-time component, which again turns out to be just in terms of space-space component. So it means that this fixes, just like we've said, this condition, by the way, which we obtained from the harmonic gauge, fixes the time-space and time-time components of the trace reverse metric perturbation in terms of the 6 independent components of that. And so it means with this, we have just completely eliminated every time component of this. Now also, if in some restricted set of gauge transformations, the generator disk, which is contained in our transformation that we wrote in the previous slide, if these are, which are of course functions of the retarded time, then the harmonic gauge then also, then with the harmonic gauge, all 4 components, that's this with xz, yz, zz, and that, are also eliminated. And of course, since this is equal to that, implies, just like we have shown already, okay, yeah, that both time-time component and time-space component can be written in terms of that, which are this ones here, like we have stated, which has been eliminated by this one. If you recall, that's what we stated. Then it also means that that all h bar mu naught are eliminated also, just like these ones here are eliminated. Okay, then it means thus the trace reverse metric perturbation and the metric perturbation are just the familiar TT gauge that we have talked about, and the only non-zero components therefore are the hx equal to minus hyy, and then of course this equal to just hyx. So in the TT gauge we write the metric perturbation as h mu nu tt in that form, and here we are going to let the h plus and h cross to be 2 independent non-zero components for the plus and cross polarization of the waves. So that in the TT gauge, it will mean that this TT is equal to minus that, and of course, for the sake of our solution, it's going to mean that this is equal to h plus of t minus z. Of course, the same is applicable for the other polarization state, h cross of that. Okay, now erasing all this, so moving in as quick and as quickly as we can. We want to recall that the tidal gravitational field is given by this. This is something we just sketchily showed in a way that from the beginning of this lecture, that this is equal to that, is equal to this, is a comma, jk is equal to minus half h naught naught comma jj. Of course, here at this point then, it will simply mean that in the TT gauge then, what this will mean is, okay, sorry, I just realized, because we have originally, just a few moments ago, stated the elimination of the temporal parts, temporal component, and or in other words, something like the space-time and time-time components. So in other words, it means we are just throwing off all that components of the reverse metric perturbation. But just here from the Riemann tensor, it means that even in our definition of the tidal gravitational field, the Rj0k0 will not be what we had written originally or initially. Of course, what we had written originally in the beginning was not here, comma jk. And if you remember then in our slow motion approximation, it was because the time derivatives will all have to vanish. And that was why the only component left was the time component. But now we are working towards the TT gauge, and so we just have to go back to the Riemann tensor and then again revisit what we have done to obtain Rj, R sub j not k naught. And so in doing that, the mistake that was made actually was to have, so if you look at what we have here, it's just looking at alpha, beta, gamma, delta. So if our alpha is j and our beta is not, and our gamma is k and delta is not, then it will mean, for instance, that I just need to substitute it correspondingly on the right-hand side. Alpha, wherever I see alpha, will be not j. And then delta, of course, was not here, so it is not here. Beta was not, so it's not. Gamma is k, so it's k. So the same thing all along. And if you see, if you look at this whole expression, you realize that if we were to throw off the time component or time-space component, the only one then that will be left will be this one, but it will be a derivative in double time derivatives. While every other component here will be zero because we are throwing off every time component or time-space component in the TT gauge, just like we've discussed a few moments ago. So our gravitational tidal field this time becomes epsilon sub jk equal to this, and equal to that, just like we have from the beginning. But then again, this time around, the JK have been shifted to this position, and the not back to this position, sort of the kind of interchange. So that in the end, what I have here could be the double time derivative of HJK in the TT gauge. So, and that is what we have. Now, looking at this then, it means if I have selected only the space components or the spatial components, remembering also that in the spatial components, if you remember, we talked about the independent components of H being just HXX equal to HYY minus HYY, and then HY this is equal to HYX. So again, of course, this is what will be reflected in what we have here. Because then if you see, if you look at this, then if this is XX, and this will be XX, of course, if I take this then to be YY, if this will have to be the minus, then I believe this should take the minus. Sorry, well, I don't have this expression, but I don't want that to be so much of a confusion. You can just revise this, rewind this a little bit, and I guess you'll be where we have written what that should be. It just means then that this being equal to that, equal to minus half H dot dot of JK, HJK double time derivative in the TT gauge. It means that our tidal gravitational field will also have just these components alone. And of course, if we just label those components like we did for these two polarizations, which we call the H plus and H cross polarizations, I just erased that a few moments ago. You can see that then this being equal to minus that is equal to this, and this being equal to that will be equal to that especially. So at this point in time, of course, where this double time derivative simply means that, then of course that is it. I think I should pause here a minute just before I hope I wouldn't be caught unexpectedly. The past few minutes of this presentation haven't been that perfect, and I hope you really bear with me. But instead of having to repeat it all over again, I just hope you try to manage it to the best of your ability. I hope, and I really, really seriously hope, and I'll try my best to make sure that everything I do next will be quite clear and lucid, so that there will be no confusions. Okay, but so far I can assure you to the best of my knowledge that all we have done so far have been correct. So in case you have any doubts, feel free to verify them with whatever sources you wish. Particularly, again, like I've recommended, the chapter 25 and 27 of the Modern Classical Mechanism by Kipton and Blanford, and this is a text they released recently. I can't remember what there is, 218 or 219, but it's quite, it's a very good resource. So from there, just make sure you are able to confirm most of the things I've said here, and I really encourage that you do that, just in case I missed anything or got anything wrong, actually. Okay, so let's continue. Recalling that this expression, which again we've written already from the beginning, we show that this is equal to 0. And we said also it could be written as this. For instance, of course, if you recall, we've shown that this part for not is equal to 0, and I not is equal to minus half the gradient of that. And then here, this is the 2x not the t squared equal to 0. Of course, that is just what this will imply, because if you recall, if I just take alpha to the 0, that's what this will mean. It will mean the 2x not the t squared plus not of this equal to 0. So this is 0 and that is 0. Now, if I choose alpha to be I, of course, what I'll be obtaining is from this part of this equation. If I choose alpha to be I, then it means I'll have I here. But then again, we know that gamma I not from what we've obtained before is equal to minus that. If I substitute that as this expression here, then I get a plus here. Okay, moving on. Then for a motion of a particle in a Newtonian potential phi, we have, of course, that this acceleration is represented or can be written as that. Now, if I compare it with what I've just obtained here from this equation of motion of a particle in gravitational field, then you can see, of course, it's just a matter of comparing these two. Well, I could write this as, say, the gradient, yes, the gradient of 1 all over 2 h bar naught of x. And this further I could write as the gradient of, just to make everything obvious, of x. And so comparing these two, then you can see indeed that h naught of x is equal to minus 2 phi of x. Now we want to make in essence, what we want to find is if really this will be the same for this. What would this be equal to? So in order to do that, we want to recall first of all that this trace reverse metric perturbation just means that this metric perturbation is the same with this, except of course for the reversal of its trace, and that is why we're writing h to be equal to minus this object here, which of course this I can write as that. And then again, if you look at this object here, I can decide to sum over mu for a start. If I sum over mu, the first component will be for mu not here, minus the mu again becomes I. And so again, for I, of course, you know that I will definitely have to range from 1 to 3. I can be not 0. And given that the Minkowski metric is diagonal, it means that this is 0. And if that is 0, then this whole object is 0. So this part of that expression is 0. So we're left with just this alone. In other words, this h that we said is equal to minus that will just be equal to minus that. Now again, looking at this object, what I can do again is sum over nu. And for the first one, I'm going to have not, then minus the nu then will be replaced with I. Now if I did that again, recall we have already said that this object is 0, so this will be 0 again, and then we are left with this. Again, of course, this part, eta not is equal to minus 1, and because of that, this cancels that minus, and so what we have managed to show here is that the trace of the metric perturbation is equal to the trace reversed component, the temporal component or the time component of the trace reversed metric perturbation. So what it means is I can just come back to the definition of what the trace reverse metric perturbation is, and then try to use this to find what h not in this case would be. It would mean for me, for instance, mu and mu here being free indices, I can select them both to be 0, 0. So that h bar not will be equal to h bar, just h not minus half, eta not h. And then at this case, at this point, then of course, if you recall, this again being minus, which is minus 1, it cancels this to make it a plus, and I can just take this to the other side of the equation. I get a minus. It will mean then that this one on the left-hand side minus that, and it will be equal to just this one left all alone. Of course, if I evaluate this, I'll simply get half of h bar not. This would then imply that h bar not is equal to twice of this. So first of all, we know that this is just equal to 2 times h not of x without the bar on it. That's what we've just shown here. But if you recall again that h not itself is equal to minus 2 phi of x, then it means that h not bar is equal to minus 4 phi of x. And of course, that's what we just have here, that the trace of the metric perturbation is equal to minus the trace of the trace reverse metric perturbation, and is equal to this object, and we have shown, of course, that it is equal to the time component of the trace reversed metric perturbation. We've shown that the h not of s is equal to minus 2 phi of x, and then of course that h bar not of s is equal to minus 4 phi of x. So again, at this point, I'd like to erase this.